Yes, it's really a pleasure for me to see that we have the entire team of researchers that want to incorporate constraint reasoning into DMN, and I always supported this idea, and now they have very specific suggestions. So, Simon, I'm looking forward to hear what you're presenting.
All right, thank you very much
share
for
your
the
screen. Your screen disappeared.
My screen's not sharing anymore. Okay, so it should be sharing, and if it stops sharing mid-presentation, don't hesitate to stop me again.
Okay, there can be a difference if you share an individual window or monitor versus your entire screen. So.
Yeah. All right. Yeah, I'm just sharing the window, so it should work, I hope. But I'll jump right in. Thank you, Jacob, for the nice introduction. So I am Simon Vandevelde, and I will be presenting the work I did today together with Bram Aerts, Joost Vennekens, called cDMN, combining DMN with constraint reasoning. So I'm a PhD researcher at KU Leuven University in Belgium at the EVICE research group. So first, yeah, here's an overview of what I will be showing. First, we'll talk a bit about DMN, then I'll introduce constraint DMN. I'll show a concrete implementation of a constraint DMN application. Then I will compare this to some other solutions, and then I'll show a user-friendly pipeline. So this doctor planning case, which I will be showing on later, is actually a case that's already been shown by Jacob earlier, and it's a challenge which I submitted to the DM community website. So if you recognize it, it's from there. So first, DMN. What DMN does well is, of course, we all know this, DMN is very readable, DMN is very intuitive, and DMN is easy to use when formalizing decision-making. However, we find that DMN is not suited for very, very complex decision-making. For example, field can express a lot, but it can easily become unreadable. There's also no support for constraints. There's no support for optimization out of the box. So we propose additions to overcome these limitations. So constraint DMN. cDMN stands for constraint DMN, which extends DMN with constraint reasoning and other related concepts, such as quantification, types, functions, relations, and optimization. And this allows us to model more complex decisions. In order to do this, we introduce new tables. We introduced 4 new tables, namely the glossary, constraint tables, data tables, and execute tables. And I will go over each of these tables one by one. So the glossary, we changed some representations in cDMN, wherein DMN only constants are allowed in columns. In cDMN, we add types, functions, relations, and booleans, and these are defined in our glossary. So for example, we have the type glossary, and this is for the Who Killed Agatha case, DM challenge. So for example, in the type glossary, we can define a type, such as the person type, which consists of strings, and these strings are Agatha, Butler, and Charles. Or we have the type number, which is an integer between 0 and 100. Then we have the relation glossary, in which we can define relations between one or more types. So for example, here we can define that person hates person, and this could be used to represent that Agatha hates Butler, or Butler hates Agatha, or both at the same time. It can show all these different hate relations, so to speak. We also allow for booleans, for example, suicide. Then, of course, we also allow constants, but the main difference with constants in cDMN to constants in DMN is that they have to be explicitly typed. So, for example, here we have the constant killer, which will always be a person. So this means that the killer will always be Agatha, Butler, or Charles. There's no one else that is in our model. Then we have the function glossary table, in which we can define a function. So this is a mapping from one type to another type. So here, for example, we have the age of person function, and this will map every person on a number, which will represent their age. So for both Agatha, Butler, and Charles, we will have an age in this function. Then constraint tables. is another type of table which we add in cDMN. And these differ in two main ways from decision tables. One, we allow sfield in the output columns of constraint tables. And two, our rows in constraint tables represent logical implications. So this means that if the input is satisfied, then the output has to be satisfied, like in normal decision tables. However, we don't say anything about the output when no input is applicable. So we don't have a default value. We don't force the tables to be null. We don't say anything about the output in case that the input isn't applicable. And we denote this table by the E* hit policy, which stands for every, as in every row needs to be valid. So for instance, here you can see a constraint table in which we state that if require healthy is yes, then the total sodium, total fat, and total calories needs to be below these three values. And we can translate this into first order logic as such. Now in cDMN, we also add quantification to our tables, universal quantification. And this allows us to apply logic for all values of a type or for more values of a type. And we do this by introducing a type as column header, and then subsequent uses will refer back to this quantified variable. So for example, in the Who Killed Agatha problem, where we want to state that nobody hates more than 3 people, we could state that for every person, so this is read as for every person, the number of hatees of that person has to be less than 3. Or we could quantify over the same domain multiple times, where we would say for every country called C1, this is in the map coloring challenge, where we want to color a map and make sure that no bordering countries share the same color. Here we could say that for every country called C1 and every country called C2, if they are bordering, if they satisfy the relation, then they cannot have the same color. We don't say anything about 2 countries when they are not bordering. We only say something when they do border. Another table which we introduce are the data tables, and this is based on the theory that typically problems can be split up into 2 parts. 1, we have the general logic of the problem, and 2, we have the specific problem instance which we want to solve. So for example, again, for the map coloring problem, the general logic would be that 2 bordering countries cannot share the same color, whereas this specific map could, for instance, be Western Europe. And this could be compared to what is already known as a relation in DMN. However, in data tables, we do allow quantification. So a data table doesn't have a hit policy, but it has data table in the name. We only allow basic values, so no complex field in a data table. But as I said, we do allow quantification, and this allows us to define a data table as such, where we say for every country called C1, which is Belgium, so actually for Belgium, and every country which is part of this list of countries, they border. We can do the same for Germany, we can do the same for every other country in our map that we want to color. Now the advantage here is that if we ever want to color in a new map, all we need to do is switch out our data table by a new data table representing this new map, where we then define what countries border what other countries. So in cDMN, we no longer have a single solution, whereas in DMN, we have a single solution for a set of inputs. In cDMN, this is no longer the case, but rather we define a solution space. And we need a way to traverse the solution space. And in order to do this, we implement the execute table. And this allows us to, for instance, ask the system to get 1 model, so get 1 solution, or get 10 solutions, or we can say get all models. Or we could also do optimization. We could find the model or the solution where the value for score is the highest, or we could find a solution where the value for score is the lowest. So that was very briefly what cDMN is and isn't. And now I will show a concrete application for the doctor planning challenge. So for those of you who don't remember from Jacob's presentation, I'll just go over it real quick. We need to have a doctor present at all time in a hospital, and we make this planning on a weekly basis. Now, every day consists of 3 shifts. We have the early, the late, and the night shift. We have 5 doctors in total, which can be assigned to these shifts, and every doctor has different availabilities, and some doctors also have special requirements. So then the rules of the specification are as follows. 1, a doctor can only work 1 shift per day. 2, a doctor should always be available for his shift. So this is based on the availabilities of the doctor. 3, if a doctor has the night shift, then they either get the next day off or they get the night shift again, so that a doctor doesn't have to wake up early after just working the night shift. And 4, a doctor either works both days of the weekend or works none of the days. This is a list showing the availabilities of every doctor. So for instance, for Fleming, he's available every shift on Friday, Saturday, Sunday. But then for Golgi, we have a special requirement that he works a maximum of 2 night shifts. And now the challenge is that a planning should be made in which every requirement is fulfilled. So now we'll go over rule by rule and show how we would implement these in cDMN. So the first rule, which states that a doctor can only work 1 shift per day. In order to do this, we implement the following glossary. We create a type called doctor, which represents every doctor. We create a type called day, which represents every day, and an integer number shift, which will be used to represent the number of shifts, of course. Then we also introduce a function called number shifts of doctor and day, and this will represent the amount of shifts a doctor works per day. So for instance, it could be number shifts of Golgi and Monday, and then it would return, so to speak, the value, the amount of shifts that he works on that day. If we want to introduce this, or if we want to implement this using a constraint table, we would simply do as follows. We state that for every doctor and every day, the number of shifts of doctor and day needs to be less or equal to 1. And this way we can make sure that no doctor works more than 1 shift. All right, then rule 2, a doctor should always be available for his shift. In order to do this, we introduce the type shift type, which represents the early, late, or night shift. We introduce the function assigned doctor of day and shift type, which will be used to represent whether or not a doctor is assigned to a specific day and shift type. So this could, for instance, be Golgi assigned to Monday, the early shift. And we introduce the relation available doctor for shift type and day, which will be used to represent whether or not a doctor is available for a specific shift type on a specific day. To implement this in a table, we simply do this as follows. We state that for every doctor, for every day, for every shift type, if the doctor is assigned to the shift type on this day, then he needs to be available. So we don't say anything when the doctor isn't assigned to this day or shift type, only when he is assigned to this specific day and this specific shift type over which we just quantized, then he needs to be available. And the third rule, if a doctor has the night shift, they either get the next day off or the night shift again. This was by far the hardest rule to implement. And in order to implement this, we add a new function called next day of day, which will represent the next day for every day. So for Monday, this will be Tuesday. For Tuesday, this will be Wednesday, etc., etc. And then to implement this in a table, in a constraint table, we do it as follows. We state that for every doctor and every day D1 and every night shift type, if the doctor is assigned to D1 and this night shift type, then he can only work, so then for the next day, he can only work the early or the late shift. So the doctor who works the early or the late shift the day afterwards cannot be the doctor who already works the night shift, is what this table is trying to represent. And again, this might seem like a more difficult table, but it's still a very DMN-like table. And by studying it for a little while, it easily becomes readable. So then rule 4, which states that a doctor either works both days of the weekend or none of the days. To implement this, we don't need to add anything to our glossary. Our glossary is almost complete. And we just add the following table. We say that for every doctor and every Saturday, if that doctor has 1 shift on Saturday, then he also has to have 1 shift on Sunday. And we do the same for Sunday. If the doctor has a shift on Sunday, then for every day D2, which is a Saturday, he also needs to have 1 shift. And this way, we can make sure that a doctor always works both days of the weekend, or of course, none of the days. Then we have a special requirement by Golgi. Golgi only wants to work at maximum 2 nights. And to do this, we implement the function number nights of doctor, which will, of course, represent the number of night shifts a doctor has. And then we simply add the following table. We state that for every doctor. If it's Golgi, his number of nights has to be less or equal to 2. The availabilities of every doctor, we simply add those to a data table in which we state that, for instance, here, for Fleming and the early shift on Friday, he is available. For the late shift on Friday, he's also available, etc. Then we have 3 more tables, which I haven't shown yet. This is the table to represent what the next day is for every day. It's fairly trivial. Then we have a table which will actually count the number of shifts per day. And then we have a table which will count the night shifts for every doctor. Yes. So this is our full specification of our doctor planning. So we were able to implement our doctor planning challenge in 9 decision or constraint tables and 3 glossary tables in total. And as you can see, it's a fairly small model, but yet it's able to implement a fairly difficult specification, a fairly difficult challenge. So I will now compare it to the other solutions, which were submitted to the DM community website on the 10th of June when I created these slides. These were the solutions. So there were 5 solutions in total, but sadly, none of these were DMN-like implementations, so to speak. So if we look at OPL, here we can see the rule that said that if you have the night shift, you need to get the next day off or the next night shift again. And it's actually pretty interesting. They implemented it in the same way as we did. Here they state that if it's the night shift, then he can't work early or late the next day. It's similar to what we did. This is it in Zimple or ZIMPL, I'm not so sure. And then, of course, we have Jacob's implementation, which he's already shown off earlier. And what is cool about this implementation, as he has shown, is that he created this full-blown GUI for it, reasoning that, okay, we focus a lot on making the implementations, but we don't build an application around it. Now, this GUI is very intuitive and the system works well. But I think that the main downside still is that the solver works in Java, in the Java solver. So if you ever want to change anything radically to it, it's only accessible to the software developers, this implementation. So the planner in the hospital themselves, they won't be able to switch it up, or they won't be able to change anything if they need to, unless, of course, they have this knowledge of how the Java solver specification works. So I will be showcasing our own user-friendly pipeline from cDMN to an interface. So I will be showing the auto-config user interface, in which is an interface also developed by a KU Leuven research group, in which users can interact with the cDMN specifications. Users are able to set values and they can instantly see the results. So in this way, it's interactive. I will show this off later. The system doesn't distinguish between inputs or outputs, and the system is capable of finding optimal solutions. So I prepared a demo video. I'm sorry, it's not a live demo. I was too scared to set it up. But here is the entire interface, where, for instance, we can see that Fleming isn't available on Monday because he only works on the other days. Now, we can select Heimlich to work the early shift on Monday, and then he can no longer have the second shift on Monday. And here, the constraint, the explanation says why he can't work. And then if we select Eustachi to work on Monday late, then Golgi has to work on Monday night because all the other doctors are not available. And we can ask the system again to explain why a certain value has been set. So say that this is all the requirements that we wanted to set. We can now click Model Expand, and this interface will complete the solution to a full specification or a full solution conform to the rules which we created in our cDMN specification. So you can see all the green bars. So we can reset our choices. And of course, we can do some other stuff with the interface as well. For instance, we could say that Fleming works no night shift, Heimlich works no night shift, and then the other doctor also works no night shifts. And the system concludes, of course, that Eustachi and Golgi have to work the 7 nights together, and this makes sense. So if we then say that Golgi can't work 2 nights and Golgi can't work 0 nights, then Golgi has to work 1 night, Eustachi has to work 6 nights. And then we can explain this, or we can ask for an explanation, and then the system will return us why Usagi has to work 6 nights. Now, in this case, this is fairly trivial why he has to work 6 nights. We can easily see it. But here it says that all the other doctors aren't available, so Usagi has to work these days. Of course, all the other rules are also still applied. For example, if we state that Usagi works the early shift on Saturday, but he can't work the early shift on a Sunday, then this means that he will have to work the late shift on the Sunday. And this is what I mean by interactivity. If we set a value, we can instantly see what the result is on every other value. And again, this is just by the cDMN model, which was converted into a specification for this interface. And if we say that Golgi works the night shift on Sunday, then he also has to do the night shift on Saturday because of rules 3 and 4. So in this way, a user can set some of the preferences for the week. It can set any preferences for the week, can then model expand the system, and then the system shows a full, complete solution to this cDMN challenge or problem. All right, so that was my demonstration video. I would like to thank you all for your attention and for your explosive chats in Slack. If there are any questions, I think there might be, feel free to ask. I have listed some information here if you want to read more about cDMN or about the interface which I've shown. Yeah, so thank you for your attention.
That's great, Simon. I figured you were probably watching the Slack channel when I put in that comment about those being fighting words at the beginning. I saw you chuckle, so.
I should turn off my notifications.
Yeah, you have to turn off the notifications when you're on a presentation, otherwise it's just too distracting. Denis pointed out that SFEAL is deprecated from DMN now. And it's interesting, if you look at the discussions going on in the Slack channel, Denis says, this is an interesting approach to modeling constraint problems, but why do you use the name DMN? Because it's not DMN notation. But then Bruce Silver pops in and says, actually, all of your tables are already in DMN except for the constraint table. So the extension to cDMN is simple. So there's, I think they both liked what you're doing, but are arguing over whether it should be called DMN or not. Do you have any comments on that?
Well, our main reason for calling it cDMN is that I should first say that we are not trying to build a system to replace DMN. Of course, I think that's obvious. This is more of a system which could work side by side to DMN, where for some use cases you could use DMN, for some use cases you could use cDMN. And now we simply named it cDMN because we based it on DMN, standing on the shoulders of giants. We based it on DMN and we just added the constraint table. And then once we added those constraint tables, we added the more and more. We added the quantification, we added the data tables, we added the execute tables. So our initial, the thing that we initially wanted to do was to add constraint tables, but then we followed up with all this more related constraint reasoning concepts which we added in. So that's why it's called cDMN. But of course, what's in a name? I don't think it really does matter that much. It used to be called DMN Plus until Jan van Tiene told us that that sounded like it would replace DMN, which is, again, not our intention at all. So we renamed it to cDMN.
Right.
But I have already bought the domain, so.
Matteo says that it's an interesting extension of DMN-like modeling to represent constraints. So maybe think of it as an extension as opposed to, like you say, you don't want it to be a replacement.
Yeah, no, it's definitely not a replacement. Because, of course, there are some use cases where cDMN would be completely overkill, where you don't need all this. I mean, all of you can prove me that there are such use cases. But it's just for our specific use cases, we were missing those constraint reasoning concepts, which is why we extended DMN to cDMN.
Right. Jacob wants to know if you would suggest mixing your tables with other DMN tables or boxed expressions within the same decision model.
We could, or we do actually mix with other DMN tables. For boxed expressions, we don't really support boxed expressions so far. And I don't think whether that's 100% necessary, seeing as the quantification and the constraints can replace a lot of what boxed expressions can do. At least that's the case in my opinion. And that's how we've seen it in the past when we've applied this to practical use cases.
Just
where,
consider simple multi-hit decision table.
Mhm.
Do you think a constraint solver can handle it?
Well, it depends on how big the model is, of course.
No. It's just simple two rules inside multi-hit table. And so far, as I put it before, constraint solver cannot handle this because of monotonicity constraints.
No, that's true. There are solvers that are able to do it, but the one we use isn't. So
no solvers wouldn't. That's my question. Probably you should split to two different models, one constraint model and one non-constraint.
Yeah. That's a possibility. But also, for the C table, which I think creates the list, it would be possible to represent that in our solver using the relations, where we say the output of this table, we will aggregate them in one relation. So where you would normally create a list, we would create one relation, and that has all the elements in it. So it could replace those things. I think there are workarounds for most of it, but I'm not sure, again, if that's worth going into, because we haven't found practical uses for those yet in our use cases.
I just want to suggest you to submit your solutions to DM community, because our challenges don't have deadlines. So then people can see what you're actually suggesting, and maybe even you can deploy it. I guess it's open source, so everybody can try it, right?
Yes, indeed. I've been working on the models, on creating them on the cDMN website. I think there's about 5 so far, and I was going to submit them once I did this presentation.
Okay.
So I will be submitting them soon.
Good.
I also have all the challenges which we made. They're in a giant Excel file, and they're also available on the cDMN website. You should find a download link to find all our cDMN models.
So just along the line of the idea of this being an extension, Falco points out that DMN comes with an extension mechanism that would allow you to combine this with regular DMN elements in the same model. So there's it doesn't sound like there's any barrier to doing that.
Yeah, exactly.
There was a question from Lloyd about what's returned if the constraints yield a null result.
If the constraints yield a null result, then no model is returned. If the constraint, our solver does not yield null results, as far as I know.
No, but your solver can fail, and when it fails, it goes to try to find another solution, right? It backtracks, and so this is called, in constraint programming, there are no null results, there is a failure. And then you go to explore all other possibilities. Remember, Simon said that it has not one solution, but a space of multiple solutions. And when it exhausts all possible solutions, it will report that your problem is over-constrained.
Yeah, that it's unsatisfiable. Exactly. Also, Jan van Tiene mentioned the hamburger problem, which I've shown in my RuleML presentation. That's also implemented on the cDMN website. So if you want to look at that, you can find it there.
Okay, that's great. Well, if there aren't any other questions or discussion, it looks like there's a little bit of a discussion going on in the Slack channel, so we can you can definitely follow up with that. I know that we started early, so we can just have just a mini break now while we get set up for the panel. I think we still have one of our panelists missing in action, but I will put up some information slide to just show you what's happening with the panel and what we can expect from there. So if
Thank you.
All right.
Yes, thank you. Thank you very much for that, Simon. It was great.